Okay, just suspend few minutes with this diagram. This is extremely important. Why it is so? Let's understand. This is really linked with the question that has been asked. So you have been given, one is a vapor solid equilibrium, another is a liquid vapor equilibrium. So let's see the three lines over here. This is a solidus line, this is the liquid line, this is a vapor line. What these lines, each of these lines means, let's understand. The free energy variation with respect to pressure. The free energy variation with respect to pressure at a given constant temperature. Please understand that. So, I explain why this is a dash line, why this is a dash line, why this is a dash line. I'll explain everything. Let's look at it. Okay. So, a material normally, let's say, exists in three forms: solid, liquid, and vapor. So, if you increase the pressure of a material, so solid will be the most stable phase, right? We all understand this. Liquid will be the next, and at higher pressure you won't have vapor, it will convert into solid or liquid. So accordingly, if you just see the solidus line, as pressure increases, please note here, as pressure increases, solid has the least free energy from here to here. Okay? At a higher pressure, solid has the least free energy between solid, liquid, and vapor. Okay? Liquid has an in-between free energy between solid and vapor. The free energy versus pressure variation. And the vapor has the minimum free energy as a very low pressure and a very high energy at a higher pressure. Higher free energy at higher pressure. Lower energy at low pressure, higher free energy at higher pressure. So always your system will remain at a state which has a minimum energy. So at a very high pressure, you can see that it will be the solid line, and at a very minimum pressure, it will be the vapor. It will be the vapor that will be the most stable phase, and in between somewhere else, it will be liquid. Let's understand now this. So if I talk about a vapor solid equilibrium, I won't consider this liquid line. Don't consider this liquid line here. I'm talking about a vapor and solid equilibrium. So if you just keep a solid in the atmosphere, there is some amount of, if it is at equilibrium condition, if you can establish an equilibrium condition, some amount of vapor will be there of the material, which will create a pressure on the solid substance to maintain an equilibrium. So if you increase the pressure, the vapor the vapor will condense into solid, and if you decrease the pressure of the system, the solid will convert into vapor. So if I talk about line 1, 2, 3, and I'm talking about solid vapor equilibrium, solid vapor equilibrium. So I'm talking about line 1 and line 3. Don't consider the line liquid now. Line 1 and 3. So there is an intersection point, right? If I plot the free energy versus temperature of the vapor and plot the free energy of the solid versus pressure, let's say it's in a straight line. Let's say for this is the plot, and there is an intersection between line 1 and line 3, this point. What this point means? This point means that for a given temperature, for a given pressure, the solid and the vapor are at equilibrium with each other. No change. The solid will remain as solid, the rest of the solid and the rest of the vapor will remain as vapor. So this is what we talked about in the earlier slide. So it's a vapor solid equilibrium. Similarly, if you talk about a liquid vapor equilibrium, we'll consider the line, let's say liquid vapor equilibrium, we'll consider the line 2 and 3. 2 and 3. Here, at a higher pressure, again you see, liquid is at least more stable than vapor. So if you are talking about a liquid vapor equilibrium, liquid is more stable than the vapor. So liquid will be more stable than the vapor. So this phase will exist, vapor won't exist. So this will be a solid line there, and this will be a dotted line there. Okay, understood? So for this, there will be a minor change here. This will be a solid line, and this will be a broken line. Okay, accordingly I will change. It's a liquid. Okay, so liquid, solid, and here is the vapor. Liquid, solid, and vapor. Vapor at a higher pressure, liquid at least has lower free energy than the vapor, and at very low pressure, vapor has a lower free energy than the liquid. So vapor is a stable phase at a lower pressure for a given temperature. Liquid is a stabler phase at a higher pressure for a given temperature. So there is also intersection between 2 and 3. 2 and 3. This is the point of equilibrium between liquid and vapor. This is the point of for 1 and 3. This is the point of equilibrium for solid and vapor. If I separately plot this part here, I don't think it's feasible. It's very important to understand this concept. So how it will look? It will look like this. This is vapor, this is solid, and this is liquid. G versus P at a given temperature. So this is for the triple point. No, it has been asked, to find out the triple point of M. Triple point of M means where vapor, solid, and liquid will coexist. That means the free energy of vapor, solid, and liquid are same. So this is the point of equilibrium between 3 phases. So we call it an equilibrium, triple equilibrium point. Vapor, solid, and liquid. Okay. So understood. This part is understood. These are 3 lines: solid, liquid, vapor. So this is the point of equilibrium. Okay. Now let's move on to this. So I have taken the solidest line, the solid line of liquid, the solid line of solid, and the solid line of vapor. If you plot these 3 lines together, you have a triple point. Okay, fine. Now let's go to the problem. Okay. Now it says that you have to find a triple point, right? How do you find a triple point? The moment it says a triple point, that means that the pressure is constant. Let's say it is P. So I have two equation. Ln P for vapor and solid. Ln P is -34000 by T minus 0.85 T plus 21.46. Okay, this one. And for vapor and liquid, I have ln P is equal to -3300 by T minus 0.85 T plus 20.31. Right? So for vapor and liquid and vapor and solid, I have these equations. So for a fixed P, that is a given pressure, I need to find the point of equilibrium between amongst all three phases. So the pressure is constant. So if I just equate this equation, what it will give me? It will give me a temperature at which it will give me a temperature at which the solid, or I can say like this, if I equate this pressure and this pressure, so the pressure, vapor pressure of the material on the solid is equal to the vapor pressure of the material on the liquid. So I can say there is a point, basically it looks like this. So I am solving this equation for a particular P. If you just look at the equation of pressure versus, it follows some exponential curves. So it is like this and like this. Okay, P versus temperature. So basically I am solving for a particular P and find out the corresponding temperature. Okay, from this equation. These are the plot. Okay, here will be vapor, here it will be at higher temperature, it will be vapor, liquid, and this is solid. Solid, liquid, vapor. Okay, so here with the pressure, no, and the temperature is a fixed temperature, or it can be anything. So I'm trying to find this point. So if I equate this equation, so I'll get a temperature where this P and this P are same. Okay, the pressure exerted by vapor on liquid and vapor on solid are same. So this is the point it should be, right? Where the pressure is constant for this, both these two lines. So that is the point of equilibrium for you, right? Let's equate this. If you equate this, this cancels out, and if you just do a transformation, if you just equate this one, okay? So 1 and 2, equating 1 and 2, log P cancels out. So it will just be, it will be 1100 by T is equal to 1.15. Okay, T is the temperature. So if you solve for T, you get 1100 by 1.15 equals to, the answer will be 956.5 is almost equal to 957 K Kelvin, right? So 957 K. So this is your answer. Please find this answer. 110 by 1.15, it will be almost 957. So at this temperature, this is equilibrium between vapor and liquid for a given pressure. Right? So this pressure is same for both this material. Right. Now let's move on to the next part. What is the next part says? Next part says heat of transformation of M for liquid to vapor state transformation delta H, the temperature corresponding to the triple point. So now I am asked to calculate the enthalpy change for liquid to vapor. Enthalpy change for liquid to vapor. Now, just recall the formula that I have used. D lnp, or let's say, I just again rewrite this equation if you have any doubt. dp dt is delta H by T delta V. We have already derived it. This is a liquid vapor. Vapor is a significantly higher volume, so it will be replaced by V vapor. So if you just PV equal to RT, V vapor equal to RT by P. So if you just substitute here, it will be dP dt is equal to delta H P by RT square. So dP by P is equal to d of ln P, this differential, right? So I'll just substitute here. So d ln P dt is equal to delta H by RT square, right? D ln P by dt is equal to delta H by RT square, this expression. So if you need to calculate enthalpy, you see your temperature is given, you need to calculate the enthalpy here. So if you need to calculate the enthalpy, so you have an expression of ln P as a function of temperature. So you have to differentiate that expression to find delta ln P d ln P by dt to equate with delta H by RT square. For example, here you have the expression for vapor liquid as this, ln P equal to minus 33200 by T minus 0.85 T plus 20.31, right? Plus 20.31, sorry.